So this is a talk that I am given tomorrow to the Oxford Physics Society. It is about the project PhysLean. This is a practice version of this talk, so there's no audience, but I thought I'd record it, put it on the internet, make it available for people to watch. You can access the slides of this talk by either scanning the QR code or going to my website, josephtooby-smith.com/oxford 2025.html. If you do that, I warn you that there's one slide in this talk that looks a bit weird, it looks a bit odd. Don't worry, it's meant to be there. It just might shock you a bit when you see it on your computer. So, yes, this talk is about PhysLean, a project to digitalize physics into the interactive theorem prover Lean 4. The talk is going to be split into three parts. I'm going to tell you what this thing is, what an interactive theorem prover is. Really, this is going to be kind of the key concept that we're going to take and we're going to apply to physics. In the second part of this talk, I'm going to introduce you to the project PhysLean. I'm going to tell you what the project is all about, and it's very important to note that this project is something that you can get involved in, and this is one of the reasons that I'm trying to give this talk to undergraduates, because undergraduates weirdly have this skill set that we need for this project, and we need to take it forth. The third part is really how you can get involved, and I'm going to kind of go through and explain in somewhat detail, how can you contribute to the project given what you know. So let me start the talk by telling you what an interactive theorem prover is. But before I do that, I want you to set yourself back to July 19th, 2024. You probably woke up on July 19th, 2024 and opened your computer. And everything probably worked fine. But on this specific day, a lot of people were opening up their computer and things weren't particularly fine. In fact, they were seeing what looked like this. This is called the blue screen of death. It happens on Microsoft computers when something catastrophic goes wrong. In this case, what had gone wrong was that there was a piece of antivirus software that was operating in a protected part of the computer, something called the kernel. And that bit of antivirus software had an error in it. And that error was something that Windows could not close. The result is this blue screen of death. Now, it's very unlikely that you saw this on July 19th, 2024. And the reason was that this malware software wasn't really used by personal computers. It was more used in big computer, or people with big computer networks, such as governments, hospitals, airports, etc. The company that made this software probably wasn't heard of very much before this day, but after it became infamous. And the day became called the CrowdStrike incident, or the event became called the CrowdStrike incident. It affected 8.5 million computers worldwide, across the economy $10.5 billion US. It's quite a lot of money. And it was ultimately down to this thing called a bug in code. That is like a mistake or a typo in code that means it runs, but it doesn't run quite in the way that you think it does, or it doesn't run at all. And if you've ever tried to program something, you have probably experienced bugs in code, and most software have bugs in them. Some cause shutdowns of governments, others just cause a pain. So why am I telling you this story? That'll become apparent in a second. But before I tell you why I'm telling you this story, I want to tell you another story. But let me ask you a question first of all. Have you ever made a sign error or a factor of two mistake in a problem set or a paper, or whenever you're trying to do physics or maths, have you made such an error? The answer to this question is almost certainly yes, because these sorts of errors are very prevalent in physics. They're very prevalent in mathematics. They happen all of the time. They're just basically down to humans being slightly careless when we're doing calculations. We don't necessarily go through it in the fine detail. We're often thinking about the more big picture sort of stuff. So if you're an undergrad, you've probably made these sorts of mistakes in problem sets, but these sorts of mistakes happen not only at the level for undergraduate or master's students, but unsurprisingly, they happen in research level physics as well. And to demonstrate this, I want to tell you a story about a paper. This paper was published on the archive. The archive is something like it's something called a preprint server. So this is where academics put papers before they go to journal and before they go to peer review. The paper in question is HEP-PH 05122212. Doesn't matter what that is. You don't really need to know the content of this paper. But it is this paper here, a QCD summary study of light scalar mesons by Hee-Jung Lee. QCD is a type of quantum dynamics. It basically governs the strong force. Mesons are a type of particle. We don't really care about any of the details. All I want you to know is that what Hee-Jung did in this paper is he calculated these terms, A1, A2, through to AN, added them together to get this quantity E. Shortly after this paper went onto the archive, another paper appeared, and I'm going to move myself over here. That paper was called A Comment on the QCD Summary Study of Light Scalar Mesons. And people often publish comments if they've tried to communicate with the author to tell them that there's an error, but perhaps there's a disagreement and they think it's worth writing another paper or comment and putting on the archive about a paper. What this comment said was that Hee-Jung had made a mistake. He'd missed two terms, B1 and B2, which when added to the quantity E, invalidated Hee-Jung's conclusions. Shortly after this comment appeared on the archive, another paper appeared on the archive. A reply to the comments on a QCD summary study of light scalar mesons by the original author of the first paper, saying, no, those terms shouldn't be there. The comment has made a mistake. The original paper was correct. You can probably guess where this has gone, because shortly after this reply to the comments on a QCD summary study paper appeared, another paper appeared. A reply to the comments on the QCD summary study of light scalar mesons by the authors of the original comment saying those terms should be there. In the end, the authors of the comment and the reply to the comment realized that they had made a mistake. They had made a typo in their code, akin to the sorts of mistakes, the factor of two errors and the minus sign errors that you may make in your problem sets. This one was slightly more conceptual, but it has the same principle behind it. And that idea and this mistake basically wasted the research time for academics over the period of about 6 months, which is how long these papers backwards and forwards lasted for. So why am I telling you these two stories? I'm telling you these two stories because they're different manifestations of the same problem. What does that mean? Well, if you think of LaTeX or Microsoft Word or even pen and paper, LaTeX being the sort of software most academics use to write papers, as computer programming languages, you can think of these typos, these more conceptual mistakes, as errors or bugs in that programming language. And if you think of it like that, you realize that the first story that I told you, bugs in code, and the second story that I've told you, errors, typos, and factors of two error, conceptual errors, and papers, are really one of the same thing. And they actually have the same solution. But before telling you what the solution is, I wanted to show you how the problem is not helped by something. So this little text box here is akin to something like LaTeX or Microsoft Word. It's basically a text editor that's going to let me write stuff in. And you should think of this as me just writing into Microsoft Word or writing something into LaTeX. I'm going to write the following. Let f be a function from nat to nat, nat being the natural numbers. So let f be a function from the natural numbers to the natural numbers, and let a be an integer, then f is equal to a. So I've written that down in this little text box, and you will notice that I made a typo, a mistake, a spelling mistake. And Microsoft Word and LaTeX have gone, that's a mistake. They've gone, that doesn't work. You have made a mistake there. And they put a little squiggly line under that, and if I fix it, it will go away. But there's something else wrong with this sentence. It just doesn't make sense. Mathematically, the sentence doesn't mean anything. It's just incorrect. You can't set a function from the natural numbers to the natural numbers equal to an integer. This would be akin to setting, for example, the function that squares every natural number and setting that equal to 3. It doesn't work. It's like comparing apples and oranges. But LaTeX or Microsoft Word, or your pen and paper. It doesn't know that you've made that sort of mistake. It has no way of knowing you've made that sort of mistake because it doesn't know the contextual information behind the thing that you've written. For all it can see, these are words and strings, but in fact, they have additional mathematical content. And the same is true when you're writing a programming language, something like writing things something like Python or C++. So what's the solution? Well, the solution, so what's the question, Rafa? What if there was a way to guarantee your code or your problem sets or your papers are correct? What happens if there was a way that perhaps Microsoft Word could have seen that that was an error in the thing that I wrote? And this would solve that problem of typos and bugs in code because you wouldn't be able to write them down because you would have a way to guarantee you didn't have these sorts of mistakes. And there is a way to guarantee this, and it is to use this thing called an interactive theorem prover. An interactive theorem prover is a programming language, like Microsoft Word, LaTeX, or pen and paper, or like C++ or Python, where you have a guarantee of correctness. It's something called correct by construction. It means that you can write stuff down and you can be absolutely sure that you're correct. And in particular, in an interactive theorem prover, you can write definitions, you can write theorems, you can write lemmas, you can write calculations encoded as theorems, and you can write their proofs. And you have a guarantee of correctness. You can also write software and have a guarantee of correctness within that software. There are a number of interactive theorem provers out there. There's Rock, there's Isabelle, Lean, and Agda, and they all serve slightly different communities. Rock serves a community of mathematicians working on this thing called multiple type theory. We don't really need to go into the details of that. Isabelle is kind of used fairly generally. Agda is used particularly in the computer science community, and Lean is used by the mathematicians and the theorem provers, and as we'll see, the physicists. So I wanted to demonstrate a little bit about how these interactive theorem provers work. And to do that, I need to come out and I need to refresh. So this is what Lean looks like. This is an online portal for Lean. And if you are following along, I really encourage you at this point to follow that link down at the bottom, come to the slide and code with me. Because if you do that, it's going to make a lot more sense. I should caveat this with what I'm about to say can be a bit technical and it can look a bit confusing. So if you don't understand anything I'm going to say for the next slide when I'm doing this demonstration, do not worry. It doesn't, what I'm about to say in the rest of this talk really does not matter about this slide. But if you understand this slide, it will help you understand a lot better what is to come. So I want to show you, the first thing I want to show you in Lean is that if I write that sentence that I wrote in LaTeX or Microsoft Word, I want to show you that you get an error. The same sort of error that you would expect if you made a spelling mistake in Microsoft Word. So what does that sentence say? Obviously, I can't write the sentence in the same way. I have to use some syntax, but this is all this is. I'm just going to say the same thing, but I'm going to say in syntax. So I'm going to say example. We're going to say let f be a function from the natural numbers to the natural numbers. And to write this backslash, this arrow here, I've done \2, and then I've done space. And I'm going to say let a be an integer, and this is how you write a as an integer in Lean. And then I'm going to write f is equal to a. And then I'm going to finish the line by doing sorry. And you will notice that when I write this sentence down, I get a little squiggly red line under the a. The same sort of little squiggly red line that I got under that function when I misspelled it. But this one isn't telling us that I've misspelled something. This is telling us that I've made a mathematical mistake. It is saying you have done something that is not allowed in mathematics. You have set a function f to be a natural number a. And if we all hover over this a, it basically says this exact thing. The type of a is of an integer. So a is an integer, but it's expected to be a function because you've set it equal to a function, but it's not a function. And this is where you have, and this is why Lean is so powerful, because it doesn't let you write things that are mathematically incorrect. Lean works on this thing called type theory. Type theory is like set theory, and for the purposes of this talk, I want you to think of a type really as a set. It's not exactly the same, but just for convenience, we're gonna think of types as sets. And what I'm going to do is I'm going to show you how you can define, for example, the natural numbers in Lean and how you can prove things related to natural numbers. My aim here is to kind of give you a basic understanding of what Lean looks like, what you can write in it, what you can do in it, and all of the powerful tactics that you have. Again, don't worry if you don't understand this, just kind of hopefully you'll get the idea that you can write things in Lean and you will check for mathematical correctness. So I'm going to define a type called mynat, and this is going to correspond to the natural number. So you can think of a type as a set. The only real difference is that for a type, you specify its element. You specify or you define it by specifying its elements. So we're going to define this type mynat, and we're going to define it by saying what the elements of that type is. So we can give it the element 0, for example. Okay, because we expect the natural numbers to have 0 as an element. So we can say, okay, we want to type mynat to have the element 0. So you'll notice that Lean doesn't complain about this. And this means that this is a perfectly valid definition. It's not the definition of the natural numbers, but it is the definition of a type with a single element that corresponds to 0. So what other elements of the natural numbers do we have? Well, we've got 1. I think that's the next natural number. So we could go 1 here. What else do we have? We have 2. So we could go 2. So on and so forth. How long do I have this talk? Because I could just, keep on going. Well, okay. It turns out you don't have to write down every little element explicitly. You can be more clever, because in Lean you can define things inductively. So what does that mean? It means that you can define the natural numbers by saying you have the natural number 0, and then for every natural number you have another natural number called the successor of that. So 0, we have a successor of that, and we're going to call that 1. We now have 1, but I've said that for every natural number you have a successor. So we have the successor of 1, which is 2, but now we have 2, which is a natural number, and so on and so forth. So you get a natural number 3, and so on and so forth. So the way that you write this in Lean is you're going to say we're going to make an element of this type, and we're going to call it sec for successor, and we're going to say it takes in a natural number and it spits out a natural number. So the successor of a natural number is basically the same as that natural number plus 1. Once you've got a type, natural numbers, you can start to define other types with them. You can start to define more complicated stuff. So we have this type of natural numbers. We can use that to define functions between types. This is basically the same as functions between sets. And addition, this definition of addition, is basically the specification of a type. This maps from natural numbers to functions of natural numbers, and a term and an element of that type, or an element of that set if you're more used to set theory. So to define addition, we need to define this function, and we are going to do this. We're going to do this basically inductively. So we're going to take this first element to be 0, and we're going to take the second element, the second natural number, to be any natural number n, and we're going to say, okay, 0 add n. I need to put a full stop there, sorry. With 0 add n, it's just going to be n. Then we need to do the other case, the successor case. So we can define addition where the first number is not 0, but it's the successor of a natural number n, like this, and we're going to add it to n, and we're going to say, so what's the answer here? Well, the answer is going to be the successor of the addition of m and n. And notice that this definition is something that we would call recursive in computer science. And recursive basically means that the definition, the thing you're defining is used to define it. And this is okay because this definition terminates, this recursive call terminates, because here I have m plus 1, and here I have m. And Lean is clever enough to work out that that terminates. So this is all fairly mathematical. But in fact, Lean is a computer programming language, and you can execute these functions. So you can say, okay, I want to take addition, and I want to add the successor of 0, which is equal to 2 in our weird language for natural numbers, and we can add that to itself. And if I look on the right-hand side of the screen here, you will see that 2 plus 2 is equal to 0, add 1 success, 2 successes, 3 successes, 4 successes, 2 plus 2 is equal to 4. We can define the natural numbers in the same way. Again, the natural numbers is an element of the same type. And we can again define it inductively. So we can say 0 times by any natural number is equal to 0. And I need a full stop there. And the successor of a natural number m times by n is equal to the addition of with the multiplication of m and n. And I can just replace the n with an underscore. I'm not going to go into why you can do that, you just can. So this is the definition of multiplication, and basically in any type theory language, interactive theorem proof, this is kind of how these things tend to be defined. So these are definitions, and this is how Lean lets you define things, but also, and these are mathematical quantities, but they are also computer programming languages. There's also computer functions. So they are things that you can compute with, but there are also things you can prove theorems about. And I'm going to show you what a theorem looks like. So this is the statement that addition is associative. Associativity of addition basically says that a plus b plus c is equal to a plus b plus c. And what a lemma is in Lean is basically a type, which is this thing here, and a proof of that is a term of that type. And we could define the term kind of as we have done here, or the element of that type as we have done here, or we can define it much more nicely using powerful tactics. So here's the other great thing about interactive theorem proofers. They have lots of powerful tactics that you can use to prove things. And these tactics allow you to prove things a lot more easily in some cases than you would be able to prove them if you're doing it by hand. Sometimes you have to work more in detail than if you do it in hand, but sometimes you can use powerful tactics to help you prove things. And this is kind of a fairly unique thing to interactive theorem proofers, is they have these tactics that help you prove things. So you can see on the right hand side, we have what's called the tactic state. So this is the thing we are trying to prove, and this is what we have at our disposal. So we want to prove that addition is associative. The only thing we can really do here is do induction, because this is the only really information that we have about the natural numbers so far. So how would we do induction? Well, we type induction, and we're going to go a with, and this is just syntax. We're going to say there's two cases. There's the 0 case, and then there's the successor case. And I put sorry in some places, and what sorry does is it basically goes, I'm not going to provide you a proof of this right now, but I haven't provided you a proof. It's kind of like a placeholder when you don't want Lean to give you an error, but you also haven't found a proof. So you'll now notice that the first induction case, the base case, my tactic state has now changed. The a has gone from here, and my a has been replaced with a 0. If you think about the definition of addition that we defined up here, 0 add b is just equal to b, and 0 add b add c is just equal to b add c. So really this is true by definition, and there is a tactic in Lean called REFL that says this is true by definition. And when you call this tactic, Lean checks this. So this is not you telling Lean this is true by definition. This is saying this is you telling Lean, check this is true by definition. And if it is true by definition, Lean will be cool and it will be error-free. If this wasn't true by definition, REFL would not have worked. So if I call REFL here, it won't work because it's not true by definition. So in this inductive case, we now have this thing here, which is the goal we're trying to prove. And this is the case where we're dealing with n plus 1. And this IH thing here is the inductive hypothesis. So this is the case for just n. And we want to prove this. So how would we do this? Well, we have another tactic at our disposal, and that's called simp. Simp is basically like a simplified tactic. So we're going to do simp, and we're going to give it definition of addition. And if we call that tactic, you will notice that if I put my cursor before simp, we had n.sec, and here we just have n. So simp has got rid of that sec for us. We don't have to worry about how it did this. It probably use some lemmas. We could find out if we wanted to, but simp is a powerful tactic that lets you prove it or simplify your goal, which is this thing here, down to something much simpler. Now, if we look at this and we look at this IH, and we look at the goal, you'll notice that they are exactly the same. And there is a tactic called exact. And if we call that and we call exact IH, it proves the goal. And we have no errors here. So importantly, this is a formally verified proof of the fact that addition is associative. We can be sure that this proof is true. We don't have to worry about this. Lean, the computer, has checked this for us. Okay, maybe you don't need convincing that addition is associative, but there's lots of things that perhaps you do want convincing. I want to show you that what I've shown you so far is kind of academic, and when you're actually dealing with things in Lean, proofs can be a lot shorter and a lot less manual than I've done above. So here I have a equation in terms of integers a, b, c, and d, and we want to show that this is true. We want to prove that this is true. There is a tactic in Lean called ring. It's basically related to something called ring theory. If you've ever done, you may have done this if you've done like linear algebra in your first year. And if we call ring, the theorem is proved. And there are no errors, there are no squiggly lines. So this tells us that Lean has checked this. It has gone down to its mathematical foundation of type theory. It has checked this and it has said, this is true, all is good. So what are the advantages of using an interactive theorem prover? So if you lost me in the kind of like the last little demo, you can rejoin here, because what I'm going to say from now on really doesn't depend on that example that I gave you. But what are the advantages of an ITP, an interactive theorem prover? The first advantage is kind of the one that I've been leading this talk with, is that you have a guarantee of correctness. Everything you write into Lean is going to be correct if you don't have any errors. There's no ifs or buts. There's no, you may have made a typo here. You may have made a mistake in your proof. If Lean compiles, if it works, you're guaranteed correctness. The second advantage is you have tactic automation. So you have this tactic ring that I showed you in the last slide that proves that theorem. And you can develop tactics that help you prove theorems. So maybe you want to do Feynman diagrams and you want to prove a result about Feynman diagrams. If somebody makes a tactic for that, you could use that tactic to help you prove things about Feynman diagrams. The third thing is searchability. So unlike LaTeX or Microsoft Word or your pen and paper, Lean knows what everything corresponds to mathematically. It knows the mathematical structure of definitions and theorems. And you can use that structure that Lean knows to help search for definitions and theorems, not by what strings do they contain, but by the underlying mathematical context of these results. And this is really helpful and really useful. The fourth benefit is that everything is reusable. There is a proof of some complicated results in physics within PhysLean. You don't have to prove those again. You can use those to prove other results. Everything only has to be done once. And the fifth benefit is kind of what I showed you, is that your definitions are executable. So you have this way that you can write down definitions of theorems or definitions of things in physics, and you can use them to compute stuff, but you can also use them to prove things. So you have this interface between programs and computers, or sorry, simulations and executable functions, but also theorems and lemmas and definitions on the other side. So you have this interface between theory and computational physics, let's say. So they're the main advantages of using an interactive theorem prover, which opens the question, who is using an interactive theorem provers? Who is using interactive theorem provers? So the main people that are using it are the mathematicians. And there's one project that probably stands above the rest within mathematics in interactive theorem provers, and this is the project MathLib. MathLib is a monolithic library for mathematics formalized in physics. What does monolithic library mean? Well, it means it is a library of results that you can go to, and it covers lots of areas, most areas of mathematics, and you can go to the files within that project and you know, it tries to contain all of mathematics. And that is what monolithic here means. It kind of is an encompassing library of results from mathematics formalized into Lean. It was started in 2017. It has over these numbers are slightly out of date now, has over 500 contributors, 100,000 theorem definitions, and over 200,000 theorems. Wasn't made by Kevin Buzzard, but initially Kevin Buzzard was one of the people that helped drove it. And he's he's a maths professor at Imperial, and he helped promote it towards the start. So we have so let me go through some of the errors in MathLib. They've got things like algebra, algebraic topology, category theory, condensed mathematics, geometry, information theory, group theory, logic, measure theory, number theory, representation, set theory, topology. Lots of areas of mathematics that you probably haven't studied in your physics degree, but some of them are very important to physics, like group theory. Topology can be, if you're looking at certain types of things, differential geometry, etc., etc. So if you want to find results from mathematics in an interactive theorem proof that have been formalized and verified, MathLib is the way to go. And I'm going to show you later on that there are ways to search things like MathLib without knowing any lean. So you can get the benefit of like searching for results from this project without ever having to learn lean. The other people that are using it are AI researchers, and there's a reason behind this. The reason is that you can get your AI to try and prove a theorem. You can give it a theorem in lean, and you can get your AI to try and produce a proof of that theorem. And if it doesn't manage to do it, lean will tell it that it hasn't managed to do it, so it can change its proof. So you get this feedback mechanism from where you've got AI on one side and lean on the other side, and they can talk to each other, and that can allow the AI to, produce a proof that is correct, and it's correct because lean tells you it's correct, without a human having to go, you've made a mistake there, go and correct it, you've made a mistake there, go and correct it. Lean does that for you. And this is one of the reasons that companies like Google DeepMind have turned to lean to try and formalize, to try and reason about mathematics. And last year, Google DeepMind competed in the International Math Olympiad with their AI system, and they used lean to do it, and they got themselves a medal. More recently, this has been surpassed by people people have got gold medals this year, but less of them used lean in the end this year. So I wanted to give you an explicit example of an AI trying to solve a theorem, just because I thought it'd be fun, and I thought what better theorem to try than the theorem that we proved earlier in this talk, that addition was associative. So this is the theorem that we proved. This is kind of just more syntactically structured, and I'm going to copy it, and I'm going to go over to this thing here. So this is a online API, let's say, for one of these proof assistants that works with lean. And what I'm going to do is I'm going to delete this, and I'm going to give it this theorem. And what the AI is going to try and do is it's going to try and fill in this, and we're going to see how well it does this. We're going to give it 16 goes at this. And if any of these things turn green, then we will see that the AI has proved this theorem for us. And I believe this AI is using this kind of feedback mechanism that I spoke to you earlier today about. So I'll give it a couple of minutes. We can see that, okay, good, great. So it's already proved it. We can go, it gives us an explanation of the proof, and let's go and look at the proof itself. Good, so, okay, it's done pretty good. It basically did induction on A, which is what we did. The zero case, it didn't use ref, it used simp. I did, sure it works because it checked it, so it works. And then for this proof, it kind of did something similar. Used a different tactic to finish, and it gave the simp the IH. So it seems to have done pretty well. Let's look at one case that failed, where it didn't solve it. I mean, this, to be honest, looks very similar. I assume it failed because this just didn't work, or it gives you an error. So yeah, so you can see that this AI was pretty good at solving this lemma that we gave it. So we didn't really have to do that. This AI could have done it for us. There are lots of results in physics or in lean where you can try and get AIs to solve them, and there are different ways that you can do that. Some of them tend to be quite good at solving certain types of problems. Others tend to be less good at certain types of problems. In general, they tend to be better at solving these types of, simple problems that they have seen lots and lots than they are solving, complicated mathematical problems or physics problems. Which brings me on to the next thing, the next group of people that are using interactive theorem provers, the physicists. So like Mathlib has this monolithic library of results from mathematics, PhysLean is a monolithic library for results digitalized or formalized into Lean from physics. And this brings me on to the second part of the talk, which is what is PhysLean and what does it contain, etc., etc. So, what is PhysLean? PhysLean is a community-run project. It's open source to digitalize physics into the interactive theorem prover Lean 4. And I want to really emphasize this community-run thing. This is meant to be a community project. This is open source. It means that anyone can contribute to it. Anyone can come and suggest a change to the project, can add to it, can edit it, can try and discuss the direction that it goes and discuss the protocols that we use behind it. And it is basically like Mathlib to formalize physics. It is what is called a GitHub repository. GitHub is this platform that you often see open source software on. So it's kind of the go-to platform currently where open source software is shared. It has these things called pull requests, commits, things that allow people to contribute, collaborate on a project together in a bona fide way. So I mean, this is kind of what the project looks like. This is the go-to place to see the project. There is also a website, which is just physlean.com. But this is kind of the bread and butter of what the project is, what the core of the project is about. Most importantly, it is a project for physicists, and that means a couple of things. It means it is organized by physics. So I showed you Mathlib and the different areas that were in Mathlib. There were things like differential geometry, topology, group theory, etc. PhysLean is split into areas depending on physics, like classical mechanics, condensed matter physics, cosmology, electromagnetism. Stuff that you have probably seen, or you probably will see in your undergraduate course here. Or your undergraduate course in physics, anyway. Things are named after their things in physics. So, for example, Higgs Fek corresponds to the vector space of the Higgs boson. So the Higgs boson lives in a vector space which corresponds to C2. Instead of calling that vector space, the complex vector space of 2 dimensions, in PhysLean we call that Higgs Fek because that's what physically corresponds to. That's the physical context of the theorem or the definition. It's got physics-based documentation. In other words, we try and give that, that physics story that you'll often see in lecture notes, or if you've ever seen a physics paper, that physics story that takes you from the start to the end, tells you why you're doing it, tells you that physics context about, this mathematical equation describes this, or this does this, rather than just going, here's an equation, that's it. That's just the maths of it. We want to describe the physics, and this is done using physics-based documentation. We've got references to the physics literature. So, for example, you may have seen this textbook series called Landau and Lifshitz. We have references in the correct places to Landau and Lifshitz, and hopefully, eventually, we'll get references from the literature back to the project, referencing definitions and theorems, etc. And where possible, we have computable functions, so functions that you can actually do things with. If you're a master's student and you've done quantum field theory, you will have come across these things called Wick contractions. They are things that are the precursor to Feynman diagrams, and we have a computable, a way that you can interact with these Wick contractions computably within the project. So what is currently in PhysLean? This graph, you won't be able to see the details, but this graph describes the areas that are covered by PhysLean. The big red area on the left-hand side, this corresponds to quantum field theory. This orange area here is relativity, both special and general relativity. This block here is particle physics. Things like the standard model of particle physics, electrons, the Higgs potential, all of that sort of stuff. This thing here is string theory. This here is quantum mechanics, stuff like the quantum harmonic oscillator, electromagnetism, results related to space and time, the definition of a metric on space, etc. We've got some results related to units, classical mechanics, thermodynamics, and some other stuff which are less developed, like optics. If you're looking at this and thinking, why is optics less developed? You're really interested in optics. It's less developed because we have less people working on this area. So if you're interested in doing that, come and contribute to these areas. To give you some specific results you may be familiar with within PhysLean, we've got the classical harmonic oscillator that is derived completely from its Lagrangian variational calculus to get you the solutions and to show properties of those solutions. We've got the quantum harmonic oscillator with this infinite dimensional Hilbert space you may be familiar with, these square integrable functions. We've got Maxwell's equations, both in terms of functions and these secret things that mathematicians like to call distributions, which allow you to do things like the Dirac delta function. We've got the Lorentz group and properties of the Lorentz group. The Lorentz group is the symmetry group of the universe. It is the group that defines relativity. And we have properties of that and results related to that. For example, the definition of a fermion is related to the Lorentz group. We've got the twin paradox. You may have heard of this thing. I think this is probably taught in your first year here, where two people starting at the same point. One goes off in a weird non-straight line direction and one just kind of stays still. And the person that's gone on a weird place where they meet again will have aged less than the person that has stood still. We've got the tight binding chain. This probably may have come across in condensed matter physics. It is sometimes used, high dimensional versions of this are used to approximate graphene. We've got the CKM matrix, which governs how fermions interact in the universe. We've got something called Wick's theorem, it's a precursor to Feynman diagrams. We've got string theory, etc., etc., etc. So that's currently what is in PhysLean. And if you don't want to go learn about Lean and look at the results itself, there are search engines that can let you find results from Lean. And this is an example of one. It's called Lean Explorer. It is an AI-based search engine for results in Lean, in PhysLean. So I can type Higgs field and I get every result in PhysLean about the Higgs field. And these are formally verified, remember? So these are mathematically correct results that you can search and explore for. And you get a doc string and a Gemini summary of it. So you don't actually, you also get the Lean code, but you don't have to look at the Lean code if you don't want to. So you can kind of see what is true about the Higgs field, which is good. You don't need to learn any Lean to do this. You can search for results like Maxwell's equations. I believe this is slightly out of date, which I apologize for. I did not make this. And updating, keeping stuff like this up to date is kind of a challenge, but this will give you stuff that is in PhysLean. So I kind of want to quickly show you what a file looks like within the project. So this is the classical harmonic oscillator file. This is something I kind of have explained briefly in the past. And, it's got this big doc string at the start, which explains, what the classical harmonic oscillator is all about. If you wanted to get involved in the project, you could help improve these sorts of doc strings. It's got a table of content, and then it's got stuff like, okay, the definition of the harmonic oscillator is kind of the input data, the mass of the particle, the spring constant. We've got results related to the spring constant. We've got then the definition of the angular frequency, results related to the angular frequency, the definitions of the energy, the kinetic energy, the potential energy. We've got results related to these, for example, the differentiable with respect to time. If your trajectory is differentiable with respect to time. We've got the derivatives with respect to time. We've got the energy and its derivative with respect to time. The Lagrangian, and eventually I'll show you, the variational gradient of the Lagrangian is defined like this. And then from that, you can get an equation of motion, which is just a variational gradient is equal to 0. You get things like Newton's second law, which is this statement here, and then so on and so forth. And we've got Hamilton's equations, etc. And then we've got the solutions in the different files. So this is kind of what PhysLean looks like. We try to split it into these, little sections where you've got documentation, kind of like you would see in the textbook, trying to include this physics context within the theorem. So let me take some water. So what I want to do in this third part of the talk, I want to tell you how you can get involved. Like I said at the start of this project, this is a project where we really need, more people to get involved. In particular, PhysLean needs you. We need people from a physics background. We need undergraduates that have the motivation to help drive this project forward. This is a way that if you're an undergraduate or master's student, you can get involved in a research level project contribute to the research that's happening in the world, and you can make a contribution and you can add to the project. So I'm going to give you some ways you can get involved in the project. The easiest way is to kind of just get involved in the discussion. So join the discussion forum. So the discussion is this thing called Sulip, and I'm going to go and I'm going to show you how to go onto this. So let me actually go. So the website is leanprover.sulip.com, and you'll come across something that looks like this. It may look slightly different because I'm logged in, but basically there is a channel called the PhysLean channel. You will find it on this bar to the left. You go into that and there are discussions that happen about the project, for example, about cosmology, about, unbounded operators, etc., neutrino oscillations, sorts of stuff that we're trying to get into PhysLean eventually, or that are already in PhysLean and people are discussing the forms. So if the easiest way to get involved is to kind of join the discussion, post about something you would like to see formalized. Make sure you're in this PhysLean channel. You might have to subscribe to it if you're logged in, but that's the easiest way. You don't need any links to that, and having more people with a physics background in this discussion forum that can help is obviously really good. The second thing you can do, sorry, I have a bit of a cold, this is why I'm sniffing a bit. The second thing you can do is have write documentation. So this is what the documentation looks like, and if I go to classical harmonic oscillator file, it looks like this. And this is generated from that lean file. This is that doc string that I showed you earlier. This is this documentation, sorry, that I showed you earlier. This could be improved, and you can come over to the PhysLean project on the GitHub. You can do what's called fork the project. You can come over to the corresponding file, which would be like classical mechanics, harmonic oscillator, and you could either try and fork the repository, make a pull request that requires a bit of GitHub knowledge, or you could just make a comment on the discussion forum saying this comment, this definition could be improved, or this doctrine could be improved to this. Either way is good, either way is helpful. One requires a slight learning curve about learning GitHub, but learning GitHub is a skill that you will eventually hopefully find useful in the end anyway. So you can write informal definitions and lemmas. So these are results within PhysLean that are not formalized, but they are informal. So here is an example. It is a result which is written in English, and it is something that you can add to the project. Without knowing any lean, you can just write down, perhaps you want the next result within the series or you think the next result to be proved is this, but you don't want to prove it, you don't know how to prove it. You can just write an English statement of this result. Even if you just added this and let, me or someone else do this more complicated part, that is fine. So the structure here is that this is the description, the English description of the result. And then this is kind of like the name of the result, and then its dependencies, and then an arbitrary tag, which you could just make up. So these are ways that you can, add informal definitions and lemmas. Use your expertise as physicists to contribute to the project without knowing any lean. And this is really helpful because within the lean community, there's lots of mathematicians and computer scientists that would be keen to formalize stuff, but perhaps don't have that background in physics where they would know, what result comes next, what should I prove? You've got a background in physics, you can come and help formalize the rest. You can come and help write these informal lemmas and results. You could then, if you really want to get your hands stuck into the formalization, you could try and formalize results. And there is a to-do list of results that you can formalize. The easiest are these sorry for results, and they're just results with a sorry. This takes a bit of learning. There is this thing called the natural numbers game, which is probably the place to start when learning about lean. But again, just come to the discussion forum. Go, I'm new, I want to contribute to the project, I want to help formalize, I don't know where to start. People will come and people will help. And yeah, so that's kind of the basic ways you can get involved. And with that, I want to thank you for taking the time to watch this talk. If you have any questions, best place to ask is on this discussion forum. Otherwise, yeah, thank you for watching. Feel free to comment, start the project on GitHub and all of that.